I'm asking you to design an ADC, sigma delta ADC, or delta sigma ADC that has an effective number. Well, let me say this. What is the best way? Effective number of bits of 20 bits. This is a lot, right? And then the oversampling ratio is here. And what other information you would need? Let's say, and then you know that oops. How do I turn off this?
If we want to design one like that, we'd use like a just like a 2-mod second order modulator, right?
Right. And then depending on what are another difference. So in order to achieve a 20 bits effective number of bits, right? And I'm telling you the signal bandwidth. Let's say signal bandwidth is limited to 10 kilohertz. So if I'm telling you OSR is 32, would you be able to tell me what is the sampling frequency? This should be straightforward.
Yeah, you just your 32 over your 10 kilohertz will get you your sampling ratio, right?
Yeah, except that that's not quite there. Oversampling ratio is what? Make sure you check your textbook, right? It's not just FS over FB, it's FS over 2 over FB.
Yes, okay. This one, yeah, like the Nyquist rate, kind of.
Exactly, right. So, okay, with that one, say now we want to achieve effective number of bits 20. So first of all, for effective number of bits of 20 bits, how much signal to noise ratio are we talking about?
Oh yeah, asking me again.
Yeah.
So you can just the signal noise ratio. You could just do.
This is already effective number of bits.
Yeah, you could just do. So you got what 10 over your effective number of bits. So 10 over 20, and then this is usually multiplied by the OSR as well. Or is our signal noise ratio just again our 6.02 log 2 multiplied by the OSR?
Yeah, that's more like, so the moment we have effective number of bits, right? So signal to noise ratio is connected to effective number of bits. So the effective number of bits is what? Is whatever signal to noise ratio we have, 6.02, right? It's as if we have this.
We're missing some information, I think. I'm not sure.
Let's say here, because
quantization level, maybe.
Right, the quantization level is the actual N, in the ADC. But since I'm not giving you actual N, I'm already telling you straight, effective. So let's see, the sigma delta, regardless of which order we're going to design, right? Let me just hypothetically saying that we're putting an H of Z here. This is a very general. So here is the quantizer for the ADC. So coming back is the deck. This ADC has an actual number of bits, right? But this sigma delta, by the fact that it is noise shaping, will have an effective number of bits. And of course, this is sampled much faster. Oh, well, I should say here. The oversampling is down here, which is much faster. Delete. Okay. This effective number of bits most likely is going to be much higher than the real number of bits. And the effective number of bits is always related to the actual achieved signal to noise ratio, because the maximum signal we put is the sinusoid, that is the full scale. The full scale is the full scale of the ADC, VFS. We are putting a sinusoid, which is VFS, utilizing a full scale, right? So effective number of bits is always calculated from the real SNR. So the effective number of bits is whatever SNR we achieve minus 1.76 divided by 6.02. So physically we use n, but effectively we are almost as if we are using a Nyquist, which is a much higher n. So this is the effective number of bits. So if I'm already telling you you will need to achieve 20 effective number of bits, then this is the SNR you need to achieve, right?
Okay, gotcha.
Yeah. Again, for sigma delta, what we learn in the class is that the signal to noise ratio of a sigma delta ADC depends on a number of things. The number of things are 6.02 plus n. What is this n in this time? This n is the real n you put into your ADCs. And then you have what? You have the benefit of, this is a noise shaping depending on which order you have. This is the cost, again, depending on which order you have. We have any, do you guys recall this equation from our textbook?
It's much longer.
Yes.
And
Yeah,
yes.
it's much longer. Somewhere here, it has an OSR, right? Oversampling ratio. Somewhere here, it tells you which order you're going to do. So now that you know, let's say you have 20 number of bits, how many SNR? I can do the math here for you. So for a 20,
114 dB.
Okay. So how much SNR was that?
It's kind of a guess, but like 114,
Let's
118.
Let's see. Okay. 1 is actually plus 1.76. Okay. It's 122. Not that, yeah, not too off. This is the SNR you need to achieve, right? And then, of course, for the implementation, I need to tell you probably one more thing is that if you are going to design a sigma delta ADC, I say that the quantizer, I need to tell you the quantizer that you can use. For instance, I tell you due to the supply, we can't build anything quantizer more than 3-bit. Or I can say a 5-bit, depending on, because again, in a sigma delta situation, we have to run this thing at a very fast speed. And the supply rail is only EFS, so the quantizer, we are limited in terms of how many bits we can realistically design here. So here we are limited in our quantizer bits. It's essentially knowing that the actual quantizer can only limit it to, let's say, n is less than 5 bits. Then, what kind of order would you choose, given the OSR? Right?
Are we going off of 3 or 5?
So in this case, let's say if I say 5, then you want to maximize, right? Because the more bits you use here in your ADC, the less order of delta you have to go to. If you use an n bit of 3, you probably find another order that is going to be much higher. Maybe n of 5, you can design a 3-order, 3rd order, or 4th order that would already achieve or exceed this SNR. So I will make it clear in the exam question that the quantizer design, maximum number of bits you can use in your quantizer design is a certain number of bits. So I will expect you to draw out the block diagram and then tell me which order you're using your sigma delta to achieve this resolution. And finally, if we did achieve a resolution effective number of bits of 20, what is the minimum input signal difference that we can input signal difference? We can tell, we can differentiate. Given that, again, our full scale is 1 volt. Let's say our full scale is still 1 volt. What is the minimum input signal difference that we can discern?
Is it 1 divided by 2 to the 20?
Exactly. That is the key, right? Because the effective number of bits, it is what really determines the resolution of an ADC. So from these 2 examples, you can see what the advantage of a sigma delta is. Sigma delta can allow you to discern fine grained differences. because it has such a high effective number of bits. Even though the physics number of bits, the real N you put in your ADC is only like 5 bits. Right? And then look at our Nyquist example. We are struggling to get a 50 millivolt by putting a 4-bit. We need to increase like 5 or 6 bit to be able to discern such a difference. If you're using a sigma delta, microvolt is not a problem, right? If you do the math. Just a sideward note, guess what topology